Hello, everybody. Today we'll talk about a case study as to why we don't hear airplanes flying at 35,000 feet. So, on a clear blue sky, airplanes are a common sight. I mean, there is a phenomenon due to which the airplane leaves a white trail on a clear blue sky. You can see this, but do we actually hear them? Well, let's have a schematic. Let's say you're on the ground level close to your house and you see an airplane on a clear blue sky at 35,000 feet approximately. Well, chances are you're not going to hear it. Why does that happen? So let's look at it in detail. So let's assume that the airplane is actually emitting noise at a constant of 140 decibel and it's flying at a height of approximately 35,000 feet or approximately 10 kilometers above the ground. So here's an airplane takeoff sound. You can listen to it. So on the right, you can see the spectrograph, and we can see that it's predominantly dominant in the low frequencies. So in acoustics, we have this inverse distance law. The law states that in a free field, sound pressure level decreases by 6 decibel for every doubling in distance. So for example, if the sound pressure level measured at 1 meter distance from the source is 80 decibel, the sound pressure level at 2 meter distance from the source, which is the double the distance, should be 6 decibel lesser, which is 72 decibel. So on the right, you can see this graph of the inverse distance law. So on the y-axis, you have the sound pressure ratio, and the x-axis, you have the distance ratio. So as you can see, for every doubling in distance, the sound pressure level would reduce by 6 decibel. So let's do some calculations with the inverse distance law. So here's the inverse distance equation. So the difference in level is LP2 minus LP1, which is equal to 10 log to the base 10 of R2 by R1 the squared. So with the logarithm, you can bring the power 2 and make it 20. So LP1 is the sound pressure level at location 1. LP2 is the sound pressure level at location 2. R1 is the distance between source and location 1, and R2 is the distance between source and location 2, and DL is the difference in sound pressure level in decibel. So let's plug those calculations to our actual case study, which is we're measuring the airplane sound at 1 meter distance, and that sound is actually 140 decibels. So R1 is 1 meter, LP1 is 140. We wish to determine what sound we hear on the ground. So we know the height, we don't know LP2. So R2 is known, which is 10,668 meter. LP2 is something that we have to find, so we can use the equation to capture it. So we plug the known values in this equation and we get DL to be 80.6. Now DL is LP2 minus LP1. So LP1 is already known, LP2 is what we need to determine. Now DL is going to be negative 80.6. It's because LP2 is for sure going to be lesser than LP1 due to the inverse distance law. So if you subtract less and more, so the answer is going to be negative. So that's why DL is negative 80.6 equals LP2 minus 140. And we do the calculation, we get LP2 is 59.4 decibel. So this is the sound pressure level that would be heard, by an observer, assuming everything is okay. Now there are some challenges in hearing. First, sound has to travel approximately 10 kilometers to reach us. So in that distance, air is actually absorbing sound. Now air is absorbing predominantly in the high frequencies, so it's not a good absorber for low frequencies. So when we hear the sound, we're going to hear only low frequency sound predominantly. And human ears are not very sensitive in the low frequency regions. Now, this is because of the ear frequency response. Our ears work well, very efficiently in the 1,000 and 4,000 ranges, but not very good in the low frequency, especially when the amplitude is very low. So another thing is there's always this background noise around us. Now, if the background noise is louder than what sound we want to hear, so it's going to mask that sound. And time of the day also matters. It's relatively quiet during the day. It's relatively quiet during night compared to the day, because during the day there are lots of activities going on and night is quieter. Also, the location matters. For example, if you're living in the city versus the suburbs are relatively quieter compared to the cities. In addition to all those challenges, there are other technical challenges. For example, let's say even we overcome all these challenges and we can still have remarkable hearing. there is this finite speed of sound. Now, speed of sound at room temperature approximately 20 degrees is approximately 343 meter per second. Now, when sound is emitted by the airplane, it has to travel approximately 10 kilometers to reach an observer. Now, sound is not light. Light travels at an incredibly fast speed, where sound is much slower than light. So, if you use a basic equation of time, distance, and speed, we get a time of 31.1 seconds. So, sound has to travel 31.1 seconds from the time it is emitted by the airplane to reach the observer on Earth. So even if the plane is right above the observer, it will be only audible after 31 seconds. And in 31 seconds, the plane would have traveled a great distance. Actually, it should not be exactly 31 seconds because of the temperature difference. Now, at 31,000 feet, 35,000 feet, the temperature is approximately negative 48 degrees. And the speed of sound at that temperature is 300 meter per second, because speed of sound does depend on temperature. So at lower altitude, this temperature increases and the speed also increases. So actually there is a temperature gradient between 35,000 feet and the ground. So we'll consider an average speed of 320 meter per second for the entire distance. And if we consider that speed, this would translate to approximately 33.3 seconds of travel time. So it has only increased by 2 seconds, but this is a phenomenon that exists. So even if the plane emits sound, it'll take 33 seconds to reach the observer. In addition, as I mentioned, there's a temperature gradient. So this temperature gradient, what it does is it favors acoustic refraction. So this results in an acoustic mirage. So it's just like an ordinary mirage. Sound waves are redirected toward the lower temperature instead of the higher temperature. And the temperature is lower as you go up compared to down. So this way, the sound waves bend and go upwards. So the sound waves would never reach, would never travel downward in the first place, let alone reach the observer. So here's a video that I shot when I was traveling. So I could see this airplane moving. I don't know what height it was, but it looks like it is traveling indeed at very great height. But you can listen to it. I couldn't hear any sound that can be classified as airplane noise, but you can listen to it anyway. So all I could hear was basic wind and background noise. All right, thank you for watching this video. I hope you enjoyed it. Have a great day.